Okay? So I'd like to start with the daily problem, which I saw got some play on the piazza, so maybe people found this one interesting. It's a problem which says that it observes that eggs break when you drop them from enough height, okay? And that in particular, if we have a building, okay, there is going to be a floor, if the building's sufficiently tall, that if we drop eggs out the window from the floor F-1, eggs don't break. But if we drop them out from floor F, they do break. There's a transition from where eggs break to where they don't break. Okay? And being scientists, we would like to discover this. Okay? So the question is the following. I am giving you a certain number of eggs. I am giving you an n-story building. Okay? So it's got n stories. Okay? And I'm giving you a certain number of eggs, k eggs. Okay? And the goal is to try to figure out where the threshold is between an egg here. If we drop it out of this part, the egg bounces. And if we drop it out of here, the egg goes splat. Okay? Does everybody kind of get that idea? And we would like to use the fewest tosses to try to determine that, given that we've got k eggs. Any questions? An n-story building and k eggs. Yes? Question?
K eggs per toss? Or
k eggs total. Does it help to toss k eggs out on any one floor? No. If one breaks, they all break. Okay?
One egg, how do we do it with an n-story building?
What?
It says f of 1 comma n is n.
Okay, so let's think about how we could do it. If I give you one egg, okay, at an n-story building, how can you figure out where the transition is between where it breaks and doesn't? Yes?
Since you only have one egg, you're forced to start from the most bottom floor and move up.
Does everybody see? What I should do is toss it out this window. If it breaks, well, that's the place where it breaks, right? If not, go to the next height. Go to the next height. The first floor where the egg breaks is the transition between breaking and non-breaking. Does everybody get that? Okay. So it should be clear. Does that answer your question? It should be clear that with one egg, I can determine the critical the strength of an egg, the strength of eggs. Okay? But it requires n tosses. Does everybody see that's the problem? Now, I didn't ask for this thing. What if I give you an arbitrary number of eggs? You have so many eggs, okay, you have as many eggs as you want. How would you go and figure out what was the transition with the smallest amount of change? Yeah. If I did a binary search, that would seem like it. Does everybody get that idea? What I would do is I would go to the middle of the building and toss an egg out. And if the egg broke, well, then the transition is up here. If the egg broke, I mean the transition is down here, right? And if the egg bounced, the transition is up here. Okay? So it should be clear that if I am trying to figure out, I think I set up some notation here. What was my notation? Let's let EKN be the minimum number of droppings that will suffice. It should be clear that we have just proven that E of 1n is going to be n, right? Because you're going to go from the bottom up and keep seeing whether or not it breaks, and you still need to try it at the nth thing to figure out whether the breakage point is above it. So that's why I say n. Okay? It should be clear that E of log of n, an n-story building with n eggs, I can get away with log base 2n eggs, presumably a ceiling of that. Right? Any questions? Okay? Now, the question is going to be asking, in general, how do we find strategies for less extreme numbers of eggs that optimize this? Any questions about that? Okay? Any questions now? Yeah?
Why would you need n eggs? You could use less than n eggs since you're using...
Okay, so you're telling me, really, I could get away with log n, even if you give me only log n eggs. Okay? I could do it. Notice that however many eggs you give me, I can't do better than log n. Does everybody agree with that? So you're right. We agree that greater than or equal to log n eggs, it will take log n time. Okay? Any questions? Fine. Okay? Now, what is the question? Okay? And the key point is that if I drop an egg and it doesn't break, I can reuse it. If it breaks, somebody's got to clean up. Any questions? Okay. Now, the first question we have solved. Okay, let ENK be the minimum number of egg droppings that suffice. We agree that E1n is n. I'm saying that EK of n is n to the 1 over k. Can anybody argue with that? Or let's just think about a simpler case. When I see something like that, I immediately think that looks kind of scary. What's the simplest case of that? Yeah? K equals 2. Does everybody see that really what that's sort of saying? For k equals 2, is it possible, should it be when I have 2 eggs and n floors? Can anybody give me an efficient strategy for 2 eggs and n floors? Okay, let's try you.
It's like before you throw it from the middle half, so if it breaks, you go to the bottom half, so that's basically E equals 1, n divided by 2.
Okay, so what you're telling me is one approach is you throw an egg out the middle floor, and if it breaks, okay, then you know that the transition had to happen below it, and you've got n over 2 floors, right? If it didn't break, it's got to be above it, and you've got n over 2 floors. What you are saying, you are proposing a strategy where it is going to take basically n over 2 plus perhaps 1 toss. Is that correct? Okay. But the question, can we do better? Yeah? Okay, so what if we now instead say, let's throw them out on square root of n floor. This is the square root of nth floor. This is the 2 square root of nth floor. The 3 square root of nth floor. Ultimately, we get up to the square root of n times the square root of nth floor. What is the square root of n times the square root of nth floor? The nth floor, right? Now, what you're suggesting is let's toss them out here. If it doesn't break, toss it out here. If it does break, what do? Now we know the transition is between there and there, right? And if we do this, how many are there? We would then do a sequential search for the floor that breaks. Is that with the remaining egg? Does everybody see that idea? What is the complexity of this? We're going to spend at most square root n tosses to find the right one of these levels, right? And then once we've done it, our square root n, our sequential search, the difference between k square root of n and k plus square root 1 square root of n is square root of n, right? So does everybody see that skip every k square root nth level, and then once we find the right thing, do a sequential search? Does everybody see that that's going to be less than or equal to 2 square root n? Okay, we might quibble about what the exact bound is. But this, to me, is pretty clear that it's less than 2 square root of n. How many people see that? Okay. Now, this is an example of a kind of a divide and conquer algorithm. And you guys are used to dividing and conquering in the middle. That's why, this thing looked good. Okay? But recognize what you want when you divide and conquer this thing is balance. Okay? And you want a balance between the good case and the bad case. What was the bad case if we had tossed the egg out in the middle? Well, the egg broke, right? And in one test, well, we cut it in half, but we're now doomed to spending n over 2 work, right? In this case, kind of we're balancing the searching part for the big block with the fine search. And that's usually what we would kind of like to do. Any questions about that? Yeah? How do you know to choose square root of n and not n over k or something like that? The argument, I think, is this balance idea. Okay? recognize what might you have done. So I heard some people were up at 3 in the morning doing this or something like that on Piazza. I didn't completely understand. But one of them, if I remember correct, was saying something like, oh, let's try tossing it off every second floor, okay, until it breaks. And then we'll do the search with the other egg. Notice that the first phase is very large relative to the second phase, right? And they should have then said, well, what if we do it every third toss? And now the argument, instead of it being n over 2 comparisons, would be n over 3 comparisons, right? And so then you should say, well, what if I do it every n over 4 toss? And it should be clear that you're now tempted to try to keep increasing that, right? So I mean, what is a reasonable thought process? One thought process would be to say, well, where does this balance that? Because if you look at it, if you do it every n over 4 thing, the second eggs got to only be used 4 times, where the other egg was being used n over 4 times. So seeking balance, it should be clear that square root n is the function that gives you balance. Okay? Certainly once you see it, square root n gives you balance. Does everybody agree? Okay? And how do you know that? Well, that, I guess, takes a little bit of experience to think about it. Okay? But it should be clear that if you were jacking up this function and it kept getting better and better, you should keep jacking it up till it gets worse. Right? That much I think you should see. Any questions? And you should see the idea that you want the balance between the first phase and the second phase. Any questions about that? Okay? So this is a cool problem. I like it. But it has nothing so far to do with dynamic programming. Does it? Now what I want you to do, though, is the last part is kind of very interesting to me. It says, find a recurrence for ek of n such that to give you an exact value of what ek of n is. Ek of n is the minimum number of droppings that always suffice. Okay? Can you give me a recurrence relation that will tell me exactly how many droppings suffice if I've got k eggs? Okay? Any questions about what we want to do? First, when you're doing dynamic programming, the first thing that you need to do, including on your exams, is state what is the function you want to compute. This is an English definition of what I want to compute. What's the minimum number of droppings that, which will suffice to find the transition point when I've got k eggs and n floors? Any questions? Now, once we understand that, I need a recurrence relation. What is my recurrence relation? I've got E, N, EKN, right? Can anybody propose a recurrence relation for this? Can anyone start to think of a recursive kind of an idea here? Okay. Yes? I'm seeing E, k minus 1, no, k minus 1, k root of n. Is this the next argument, comma? K root n. Okay, so what you're doing here, what is good is this starts to look like a recurrence. Okay, how do we know it's a recurrence? It's calling itself recursively, so that's a step in the right direction. What do I not like about this? You're telling me the answer is square root of n in there. Why do we know that there's a square root n in here? I don't see any reason why we know that a square root n has to magically appear here. Okay? It appeared when we had 2 eggs, but it didn't appear when we had log n eggs. So you're assuming something about solutions here that I don't yet believe is justified. Yeah.
I misspoke. I meant like not square root of n, but k through of n.
K through of n. Okay, fine. But still what I'm seeing here is you're saying, hey, that k through of n thing seems good over here. Why don't I use it in my recurrence? What makes dynamic programming a beautiful thing is that you don't have to do much thinking. Here you're telling me, look at this. I had to think about what the answer was and I'll encode it in the thing. You're seemingly say you sort of solved it in this recurrence. What I want to use dynamic programming for is to search for the answer, not tell it what the recurrence, what the answer is. Okay? Can anybody have another idea for a recurrence? So let's just keep going on this a little bit. Any other ideas for a recurrence we might have here? Okay? What floor should I toss the egg off at? Suppose I told you I was going to toss the first egg off on the fifth floor, on the F's floor. Does that help you? Okay, what's the cost of it if we actually toss the first egg off on the F floor? Yeah?
Would it be the sum of everything above it plus the sum of everything below it?
Would it be the sum of everything above it or sum of everything below it? Let's think about this now. What if I tossed it off on the F floor? What would be the cost of it if I tossed it off on the F floor?
If it broke or...
There's the two cases of broke, didn't break, bounced. Let's call it bounced. What is the cost if we tossed it off on the F floor and it broke? Does everybody see this? And here we broke it, so we had an egg on the floor.
Cost must be recurrence plus 1.
What would the cost be? Okay. What is the cost of finishing the job up? We agree we spent one toss to toss it off on the F floor. Yeah? E of k minus 1, what do you want to say? N minus F. Let's think about it. If I tossed it off and it broke, where is the transition point? Is it above this or is it below it? If I tossed it off and it broke, where was the transition point? Is it going to be over here or over here? This one here. So now I have one less egg. How many floors do I have to search for? Just F. Now what if it bounced? Does everybody see that? If I tossed it off here and it broke, what do I know? I've got F floors left to search, right? And I've got one less egg to do it on, right? What if, on the other hand, it bounced? What was my situation if it bounced? E of how many eggs? K. I've got K eggs, and how many floors do I have left? N minus F. Does this kind of look now right? Is this the cost of finishing the job? I've still got, if it bounced, I've got N minus F floors left to do. Okay? And I've still got K eggs to do it in, right? Yeah?
So do you have to take the max of these two?
Do I have to take the max of these two? The answer is yes. If I want to know the worst case number of tosses, if the egg gods above are going to be trying to make me work hard, they are going to decide if I tossed it off on the F floor, okay, whether it broke or did not break. Does everybody see it? The worst of these cases is what does it, and you said take the max. So what I'm seeing now is, and unfortunately, maybe let me rewrite this a little bit. I'm now hearing max E of K minus 1 F E of K comma, n minus f, plus 1. Okay, does everybody see it? Let me now erase this just so it doesn't distract us. Does this start to now look to make sense as an interesting thing? Okay, if I tossed it off on the F floor, how much can I get away with? Well, I pay 1 for that toss, plus what's now left is I've got 2 sub-problems. And I'm going to pay the bigger of those 2. Yeah?
So do we have to just search through all the F's now and find the smallest one? Is that the...
Now what are we going to do with F? You're telling me, yes, search through all the F's. How do we search through the F's? What? Wait, say this again? Wait a second. No, hold on. So wait. So this says, wait, okay. I'm not sure. I didn't hear you yet. So say this again. When the egg broke, I've got k minus 1 eggs left, right? So you want to say that if I've tossed it off here, I no longer think that this. You really want to say that it's f minus 1 floors? I think I believe that, right? So getting the indices exactly right is a little bit of a more delicate thing once we've got it, right? So yeah, I think I believe that now, once we know that it breaks there, our search is really left on an n minus 1, an f minus 1 floor building. Does everybody agree with that? But the bigger question was what he said here. How do we turn this into a searching thing? What is F? Where do we want to toss the first egg out? Do we want to toss it out on the first floor? On the square root nth floor? On which egg? On the floor that minimizes this sum. Does everybody see this? So what if I now say the min over all floors from 1 to n? Okay? This is now my recurrence. Okay? Let's make sure we understand it. Where am I going to toss the egg off? I'm going to toss it off on the floor that costs least total, right? If I toss it off on the F floor, one of 2 things is going to happen. First, I pay for that 1 toss. Then I am either going to break my egg or I am not going to break my egg. And after I have done that, I've got a certain number of eggs left and a certain number of floors left. Does everybody see that? And it is now a searching problem, and the cost of this is going to be the bigger of these 2. Okay, because that's the worst case. How many people see the recurrence? How many people don't see the recurrence? Okay, any questions about that? Yes?
If we know that we can choose the kth root of n or to minimize,
Yeah.
why do we have to check all the values of f if we know what f should be?
So first of all, you're saying, well, wait a second, doesn't he know this thing? And the answer is, first of all, there's a big theta there. Does everybody see that? And that big theta doesn't, in my mind, tell me exactly what the right thing to do is here, right? This is going to figure out the absolute minimum number of tosses I need. This is giving me some kind of big O approximation here. Do you see kind of what the difference is? This is an asymptotic thing, and to be precise, I don't think I really proved that you can't do better than square root, kth root of n tosses. If I had a rigorous proof, maybe that would then narrow my search. But notice that here I don't need to know anything about kth root of n. If kth root of n is the right answer, then the minimization thing will figure that out for me. I don't get a nice closed form, but I'm going to get told you can solve this problem. How big is the Freedom Tower? How many stories does that have? Does anyone remember? Okay, in the old days, the World Trade Center had 110 stories, right? And you could have snuck in there with a dozen eggs. I believe you could have snuck in there with a dozen eggs, right? Now, for this particular value, okay, the question is, what is the minimum number of tosses you could use? This recurrence will work out that value precisely, right? And it might be sort of a big O theta-ish of the 12th root of 100. But there's enough slack there that see what the difference is. Yes? Does this require me to know what the answer is beforehand? And the answer is no. And why is it? Notice that here I have a lot of eggs and a lot of floors. Here, I'm asking a question about a smaller number of eggs and a smaller number of floors. And here I am asking about the same number of eggs, but a smaller number of floors. Okay? So I want to say that if I solve this for small values of n and k first, I have the answers to these things to help me make the decision about my final toss. Does that make sense? Yes? This 1 plus is accounting for the toss of that egg. I'm throwing an egg out on the F floor. I have to pay for that toss, right? Once I have tossed that egg, I'm going to look back there and either it broke or it bounced. And then I'm going to go into this case or that case. Okay? I don't know yet till it hits, right? But I did use 1 toss.
So both recursive calls are within that. You're finding the maximum of 2 recursive.
I'm finding the maximum of these 2 recursive calls. Okay? And that's going to be the worst case. Okay? Either, if I'm trying to minimize my number of tosses, when I let that thing go, I'm going to be rooting for a break or a bounce, right? And either I'm going to get lucky or I'm unlucky, right? The max is the worst case where I got unlucky. Yes?
So you're doing that recurrence for every value of f from 1 to n?
Yes, so I'm going to say I'm evaluating what is my thing. I'm claiming ek of n is equal to the min as f goes from 1 to n of ka-chunk 1 plus the max of the break case and the bounce case. Okay? What's the cost for if I tossed it out on the 3rd floor? It's 1 plus the bigger of the break case from the 3rd floor and the bounce case of the 3rd floor. What's the case for the 4th floor? If I tossed it out on the 4th floor? The max of the break case and the bounce case. Which floor should I toss it off on? The one that minimizes this sum. Does everybody kind of get that idea? Any questions about that? How many people sort of get? Yes, question. Could I do part 2? Well, I did part 2 to show you the square root n. Does everybody agree that for the special case of square root n? Okay. Oh, what's the running time of this thing? Okay. Well, that's a good thing. How do you compute the running time of any dynamic programming algorithm? What is it? It's the number of boxes times the cost per fill in any box, right? How many boxes are there in this problem? Let's think about it. How many possible values of E might we consider if we start out with k eggs and n floors? Okay? How many? What? Well, I'm going to be calling it with a number of eggs that ranges from 1 to k, and a number of floors that ranges from 1 to n. Does everybody see that? So how many different boxes are there here? How many? Still can't hear anybody, but how much? Kn. Does everybody see this? if I am given k choices for the first one and n choices for the second one, there are k times n boxes. Okay? How many people are confused why there are k times n boxes? Okay, why is it? Think about a box as being, these are recursive calls, remember. We want to know how many different types of recursive calls are there, because we're going to slap them in a table, right? And we need to be able to store each possible one. Typically in these things, there is a maximum value for each argument, and there's a certain, that defines the number of different choices for, for that argument. How many ways are there, if you think about it, if you have, if you have P sets of pants and S shirts, how many different ways can you get dressed in the morning? Okay? Does anyone remember the combinatorics like that? If I give you P sets of shirts, let's say you have 7 shirts, and you have 7 pants, excuse me, okay, 7 pants, and you have 5 different shirts, okay? How many different ways can you get dressed in the morning? What? 35. And why? Because it's the product of those things. Does everybody kind of see it? You've got your pants, 1, 2, 3, 4, 5, 6, 7. You've got the shirts, 1, 2, 3, 4, 5, right? For every one of these pants, you could wear it with every one of those shirts. Perhaps except this one's pretty ugly. Don't even try. Okay? But does everybody see that what's happening is it's the product of the number of possibilities in each slot? That is how many boxes you have. Okay? Any questions? Yes?
I still don't see why you're doing the min from 1 to, from everything 1 to n. If you're trying to find the minimum number that always works, wouldn't you want the maximum?
Well, what is the thing? I have the choice of what floor I toss my egg out. God has the choice of whether the egg breaks. Do you see what the difference is? Right? I want to choose the floor such that no matter which way God chooses the fate of the egg, okay, I come out as good in the worst case. Right? So I am going to pick the best floor, the floor which has the minimum worst case cost. And the worst case cost is assuming that whoever decides the fate of the eggs in the universe is going to pick the worst case. So do you see why this is a max and why that is a min? Any questions about this? Yes?
I thought that it would only be necessary to have an array of n size and then calculate and to store the minimum value of each floor.
Okay, so you're saying what is the minimum, you are saying in some sense, what is the minimum tosses to find out if the transition was at that floor? I claim it depends upon the number of eggs. Okay? It should be clear it depends upon the number of eggs because we get a different number with 1 and 2. Okay? In fact, that's a fairly common mistake in formulating these recurrences is you try not to use, you don't use enough state, enough enough power in what you're doing. But what I like about dynamic programming and recurrences is I don't want to think about what's the right thing to do. I want to try all possibilities and rest comfortable in the fact that there aren't that many possibilities. That is the idea behind this thing, right? So what is the time complexity of this thing? We said there were k times n boxes. How much time does it take to fill this box? Okay? Any ideas? Well, let's go to the recurrence. How much time does it take to look up this value in a table? Constant, right? Constant. 1 plus 1 equals 1. What's the max of 2 things? 1. Add 1 to it. 1. Once I have these guys in my table, okay, This would take constant time. Does everybody see that? And how many times will I do this? I've got this loop going around for I goes from 1 to n. Does everybody see that? So how much time does it take to fill each box? N time per box. So what's the total time? This is going to be an order k n squared algorithm. Okay? How many people see that? Okay? Number of boxes times the maximum amount of time per box. Okay? Any questions about that? Another, there was a question here. What was that?
So the min of 1 to n, that happens in the first call, or that happens in all the calls?
The min is happening in every single call. Because this outer min is telling me what is the egg that I'm tossing first, isn't it? Once I toss that egg and I see it broke, I am going to be recurring on this side, and I'm going to need to know what's the number, what floor do I toss my second egg on, right? And that is going to be, when I call this thing, what was the floor that minimized this? Okay? Any questions? So how do I find where I'm actually going to toss that first egg? I'm tossing that first egg. It's really what you would sometimes call the argmin of this. What is the F that minimizes this? Tells me where do I toss my first egg. Okay? Any questions about that? Yes?
Could this work better as a series of intervals for a number of eggs as opposed to a matrix?
You're telling me could it work better as intervals for a given number of eggs?
Like the floor 0 to 10 is the first floor break, 0 to 10 has a value of 0, and this will be stored.
You know, this is something, so you might be saying that you may find that for a certain number of floors, it may not matter. A 9-story building or a 10-story building with 2 eggs might be the same number of tosses. You want to compress that. I don't want to compress it. I am perfectly happy building this matrix, and I'm perfectly happy. Again, I just populate the matrix. Okay? What I like about dynamic programming is once you see what's going on, you're not thinking about these kind of details. I am not looking to avoid cutting into the number of floors I test. Okay? I am doing what is essentially brute force search, but letting this guide it. Any questions about this problem? How many people sort of see it? How many people don't see it and want to ask something about it? Because it's kind of a cool problem. Okay? So learning to formulate a recurrence like this is not trivial. So do I say, oh, you should have seen this thing coming in? The answer is maybe not. Okay? But there's a certain logic to formulating these recurrences. Okay? And, you know, the hope is that once you've seen enough of these, you kind of pick up on the logic. Any questions about that? Yes? There's no way of knowing whether you have the most optimal recurrence. Okay, I don't tend to worry about whether my recurrence is optimal so much. I worry about whether my recurrence is correct. So the right thing that I guess you should be nervous about is whether your recurrence is correct. Okay? Now, I'm telling you this is because basically it should be clear that I am going to toss off my first egg on some floor. And the one that I want to do, if I'm worried about the worst case, is to minimize the left and the right case. Okay? So this is sort of an argument that if you see it that way, that this is basically asking the thing that we care about. Okay? But formulating the right recurrence is what I tend to be worried about more. Okay? Any questions? Yeah? You have a recurrence that's correct answer but slower than this, you're telling me. What is the speed of your recurrence? K squared, n squared? Okay? Well, there's nothing too disreputable about that. Okay? It's not as good as this one is, but this would not frighten me. Okay? How did you come up with one that was k squared n squared? What was your recurrence?
If you have k eggs, you can drop it on the k floor, 2k, 3k, 4k.
Okay, but now you're making all kinds of problems here. You're telling me that I can drop it on the 1k, 2k, 3k. You're telling me that I have to drop it on a multiple of k. I am not telling you that. This is a kind of important distinction here, right? You seemingly, if I hear what you're saying, you're telling me you know something about which floor is the right one to toss it off on. I'm saying, and therefore you only have to look at those values. I am telling you I don't know what floor I'm going to have to toss it on. So I'm going to try all of them and pick the one that has minimum cost. Then I know I'm right. If you're telling me no, chickens don't like prime numbers, and so eggs, it wouldn't be a prime numbered floor. I don't have to test a prime numbered floor. That's clearly a risky thought, right? The way that I figure these things out, I try to make as little assumption about what the answer is and try all the possibilities. That's how I get my correctness. Any questions about that? Yes? This is just a brute force solution with storage. That's exactly what it is. Okay? Now, what are the base cases for this recurrence? That's something else you should get nervous about. So first of all, I get nervous about, what do I get nervous about with these things? I do sometimes get nervous about getting the indices exactly right. I was challenged on should this be f minus 1 or f, and that's something that usually you have to be careful about. Okay? But what are the basis cases for this recurrence? But basically, what am I doing? I'm doing a brute force search. I am trying all possible number of places to toss the first egg and picking the best one. How do I know it's right? I tried everything. How do I know it's not exponential? I stored this recursive thing so that the computation was fast. Okay? That is how I think about dynamic programming. Okay? Any questions? What are the base cases of this recurrence I should worry about? Yeah? Well, what happens if k equals 1? That seems like a good case. What is e sub 1 comma n? What is that going to be? Does everybody agree that we've decided is going to be n, right? Now, if we look at that, is that the only base case that we need? Let's think about this a little bit more before we do it. This one is lowering, both arguments. So this one is lowering the number of floors, but not the number of eggs. Does everybody see that? This one is lowering the number of floors and eggs. If we lower the number of floors and eggs, we will eventually get down to a point where the number of eggs is 1. But if we just lower the number of floors, but not the number of eggs, is this necessarily going to be it? So what other case do we need? Okay, yeah? So one possibility is, what is E of, k comma 1? Suppose I only have one floor left. Okay, how many tosses does it take? We have to be careful, decide for ourselves. If we only have one floor, do we say that it breaks, that we already know the answer? I don't think that's true. I think if we only had a one-story building, we'd still be curious if the egg broke when we tossed it out of that, right? So I would say that it's equal to 1. Okay? So if I only have one floor, no matter how many eggs I have, in one toss I can be done. This, I think, is the other basis case that I need. Okay? Any questions about that? Okay? Yes?
So should your basis be, why is it n equals 1 and not n equals 0?
Why is it n equals 0? What if I have 0 floors? Okay, you guys win. Pick a different basis case. Now I've got 0 floors. How many tosses do I need? Okay, I'm happy with that one. What's going to happen then, though, when I now ask for E of K1? It is going to give me E of 1 plus this, where I believe both of these things are going to be 0. Is that correct? So then this case would fall out of this basis case. Okay? So you're right. This is arguably a better basis case because it tells you about 0-story buildings. If you didn't care about 0-story buildings, this would be an equally good basis case. Any questions about that? Okay? You see how the reasoning here kind of works? Okay. Any questions about that? Okay. How do we fill in, just to double check this one last time, how would we fill this thing in so that we had, let's now make a table here. We agree that it's going to be an n by k table. Let's think, how do we fill this thing in so that what we have is waiting for us? Is that right? That's the other part of this kind of notion. How do I know I'm not pulling a fast one and getting into some exponential searchy thing? Well, what if I have the number of floors goes from 0 to n? The number of eggs goes from 0 to k, right? What basis cases do I know? If the number of floors is 0, it is going to take 0 things, right? So does everybody agree I've got that value in my recurrence properly? Where was my other basis case? Said that whenever k was 1, it was going to be n, right? So when k was equal to 1, as n went from 1 to 2 to 3 to 4, it looks like I did this. Am I right? Does everybody agree that that's basically right? Now, what values do I want to fill in? Okay? It would be great if 1, 2. Okay? One other case, this is a case here where we have 2 eggs and 1 floor. Yeah? When n is equal to 1, it is all 1. So we also have that. We could fill this in if we wanted. And that's fine. Right? Yeah? Okay, fine. Okay, I see. For k equals 0, you're saying these cases we don't even have, right? What other ones are these? If you look at this thing, it should look like, is there any case here that becomes redundant that maybe we want to cancel here? Do we ever care when we have more eggs than floors? No, because, right, we're never going to do worse than linear search, right? We're never going to need more eggs than floors, right? So what is the example where we don't care? We don't care here because we've got 2 eggs and 1 floor. We don't care here. We don't care here. We don't care here. We don't care here. Does everybody see that these are the values that we really care about are going to be on this side? Now, what's the first interesting case? The first interesting case is 2 eggs and 2 floors. What's the right thing to do? Well, I'm going to call this thing, and in all cases, either the number of floors and eggs is going down. So this would be 1, 1. And this would be, okay, I mean, this depends upon, this is going to be 1 less egg and a number of floors from 2 to 1. This is a same number of eggs with a number of floors that are less. Okay? My claim is I have the values that I need. I think I'm not going to go work this thing out. But my claim is that if I fill it in like this, I will have the numbers that I care about. Yes?
Could you short circuit the whole thing if you've got more than log n eggs, just return log n?
If I have more than log n eggs, should I return log n? You're determined to shortcut it. You're saying, I'm smart and I want to know what I know what this answer is, so I'm not going to do it. My thinking is, don't waste your time. My thinking is, do it by brute force. I mean, you know, I tend to think about it as a brute force thing. Fill in the entire table and everything's going to be fine. Okay? And I don't worry about optimizing it that much. Conceivably, if I cared enough later on, maybe I would optimize it. But for the purposes in here, I encourage you not to get too cute. Okay? Write out a correct recurrence, specify the base cases, and then think about the number of boxes times the time per box. Any questions? Yes? Where would I get F from? So F is going to be going from 1 to n. Does everybody see that? So F is a number of floors that I am using, right? So I'm not getting it from anywhere. I am using it as it is a variable that's iterating in the evaluation of this thing, right? Okay? This table will tell me the cost of all if I have n floors and k eggs, what's my worst case cost? This table does not tell me where to toss my eggs. Do you agree with that? Now, if I was smart, maybe I would also have a second field here, which would store what was the F that minimized my cost, so that I could then look up and see where to toss my eggs. But I'm going to go through a better, cleaner example of that when I talk about edit distance in a second. Any more questions about eggs? Okay. Try to figure it out. I consider this problem, formulating it on the harder end of the spectrum. But I still want you to see that the logic of it hopefully works out in some way. How many people sort of see where the recurrence is coming from? How many people don't see? Okay. No one's fussing about it. Okay. What I'd now like to get back to is more bread and butter stuff. So if the answer was, oh, I didn't understand anything he said, you could wash that out of your head. And now let's get back to something that I think is a simpler recurrence. But I want you to understand the mechanics of this recurrence perfectly well. Okay, and that was the edit distance problem. Remember, we talked about how for edit distance we wanted to figure out what was the minimum number of changes it took to edit a full string S into a full string T, where we were allowed to pay the cost of an insertion, deletion, or a substitution. And we claimed that the recurrence relation was the following, and this is an important recurrence relation. So if you don't get it, I want to hear a question. The claim was, if we were editing some string S into some string T, we were going to have to do something at the right end of the string. Either the last two characters matched, in which case we would just want to solve a smaller problem. Delete the last character from the first string, delete the character from the last string, and we're done. Okay? Alternately, we may, even if that happened, maybe the last two characters differed. One was an X and one was a Y. If so, we have the opportunity to say, substitute this for that, and then pay what is left. Okay? Alternately, we have the power to delete one character from the end of string T. Okay? And then solve the problem where we have all n characters of S and n minus 1 characters for T. Or we could have chosen to delete from the first string, in which case we have one less character from here and a full-length string here. What is the minimum number of changes to match the first I characters of S to the first J characters of T? It is the minimum of dij, I minus 1, j minus 1, if there's a match, or I minus 1, j minus 1 if the two characters don't match, or we can insert something into the first string which will end up meaning it matched the last character of the second string. So we could pay I minus 1, ij minus 1 plus the cost of the insertion, or I minus 1j plus the cost of the deletion. Does everybody see these are the only four things that can happen at the end of the string? Which is the best one to do? Okay, the one that minimizes total cost. Can we look at the end of the string and say this was the best thing to do? The answer is no, because it depends upon what the values of these things are. But if we have computed these guys recursively, we can take the minimum of these sums, and that is the right thing to do. This is the recurrence that gives the minimum number of changes. Any questions about that? How many people get it, understand why this recurrence works? Any questions? This is one you gotta understand. Okay? Any questions? Okay, let's go a little bit more into the programming level, almost details of this one. Because again, you're going to have to, on your homework, actually do it. Here is the dynamic programming code for it. I don't think that that's necessarily readable for you, and it's not necessarily the most readable thing, but what did I do? For every I going from 1 to the length of S, j going from length to t, I am going to figure out what's the cost of the optimal way of ending up to ij, where I end on a match, where this is a match or a substitute. Match is going to pay either 0 or 1, depending upon whether those characters are the same. Or I might end on an insert, in which case I pay whatever the cost of inserting that character is, presumably 1. Or I pay the cost of a delete, which was this. I am now going to take the min, in somewhat of an ungainly way, of these three things, and that is going to be what the cost of it is. And so I am going to store in my dynamic programming table, okay, basically the cost of I to j, which is the minimum of these three. And I am also going to store the parent, which is going to tell us whether we ended up on an insertion, deletion, or substitution. Does everybody kind of get that idea? If we had the dynamic programming matrix to fill in this cell, it's going to look at this cell, and this cell. If it came from the diagonal, this was a substitution. If it came from here, let's say it's an insertion. If it came from here, it was a deletion. Does everybody kind of see that? If we store which the parent is, we will know which of the operations did we end on. Any questions about that? This I want people to understand. Okay, so a question, yes?
Find the cost of those three, and then you save the cost of the match.
I am saving the cost of all three. This you may call clumsy programming, okay? But that's up to you. I don't have to program these days, right? But I'm taking a look at the three of these possibilities. I'm taking the min of these three possibilities. That's what this code is doing. And I am using that to set what the value of mij is, the min of these three. And the parent is either going to be match, delete, or insert, okay, the direction where I came from. Any questions about that? Now, what's going to end up happening is the following. If I compute, here is the edit cost matrix. When I go to edit thou shalt not to you should not. I want to update the Bible. How many changes does it take to do that? Right? If you look at what this matrix is doing, every matrix here is going to tell me the cost of editing a prefix of the string S into a prefix of string T. Does everybody kind of get that? According to this, it says in the lower corner, the fact that this is a 5 tells me what? It tells me that there are 5 changes it takes to get from thou shalt not to you should not. How should we do that? What are the 5 changes? Let's write that out. Thou shalt not. How do I change that to you should not? What are the changes that I need to make it you should not? Anyone want to make a guess? Yeah? I am going to delete a T is one way to do it. Change the H to a Y, probably, right? Does everybody see that I did a deletion and a substitution? You shalt. What else do I have to do to make it you should not? The A I can change, substitute to an O. And then what else do I need to do? I need to insert a U, right? So that's an insertion. And the T I'm going to substitute and replace with a D. Does everybody see that? Does everybody see that it's 5 changes to go from thou shalt not to you should not? Okay? And that this matrix tells us, the way we know that is that we evaluated this over all prefixes to fill in each cell. I took a look at my 3 neighbors around it and whether the character here, N, what was its relationship to the character blank. Okay? Any questions about that? Okay? Any questions about how you built this matrix? Okay? How would I have built it? This was an initialization condition. This was an initialization condition. If I walk down the matrix this way, I have the 3 elements that I need. Does everybody kind of see that? And I can fill this in, fill this in, fill this in, fill this in by looking at my 3 neighbors and the corresponding characters. Okay? Any questions about that? How would I go about reconstructing what were the changes that were made? This is now an important... any questions so far? One important question is, now I know that there are 5 changes going from thou shalt not to you should not. How would I figure out what those changes actually were? We figured it out by hand what those 5 changes were. But how would we reconstruct it from this dynamic programming matrix? Okay? Does anybody see an idea? Yeah?
So we begin with the 5. So that 5 comes one of which is a number, which is 566. Which will take the smallest one, which is 5.
Does everybody see that to fill this thing in, I took the min of 3 possibilities, right? If the min came from here, then that meant that it ended on a match substitution. And in fact, the fact that T equals T meant that it was a substitution, right? At every one of these cells, I filled out which of the 3 was the best way to go. That was my parent solution, right? Remember I stored the parent? Which one of the directions did I come from? By going from each cell to its parent, bop, 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 bop. Okay? I reconstruct what were the changes that were made to make one string into another. What does it mean when I go on a diagonal thing? Here and I go, it says go to the previous one, says go take the if this is the parent, the fact that this is 5 and this was 5 means what? It ended on a match. Does everybody agree? Where was the last substitution? I claim the last substitution was right between these guys, right? The parent from here goes in a diagonal way, but that's not so good because although it goes in a diagonal way, the cost went up. This is where, if you look at it, we did the substitution from the D to the T. Does everybody see that? At some point, we go up here, substitute, substitute, we make a zigzag. Does everybody see that? What does this zigzag mean? The zigzag from the 3 to the 2. 2 to the 3 meant what? Meant that we inserted the O. Does everybody see that? A rightward, a leftward movement was an insertion of the O here. We had to deal with the extra O there, right? And ultimately going up this way, we had to deal with the extra T versus this, right? This was the deletion of the T. This was the deletion of the O. By following the parent's path back, we reconstruct the sequence of operations that were involved in the edit distance. Any questions about that? How many people see what I was doing? How many people don't see what I'm doing? Okay? This is why we stored over there the parent. Okay? This is why if we wanted to figure out where did we toss the egg, we should have stored what was the floor that minimized this. Right? Any questions about that? So how can we reconstruct the path? This is kind of an interesting thing. Suppose we know, again, in our dynamic programming matrix, we've got a matrix of, length of the string by length of the string. We care about the final goal state. We want to walk backwards following the parent pointers. Okay? Yes?
So, just to clarify, the point of storing the parent is to be able to reconstruct the path?
The reason for storing the parent pointers is to reconstruct the path. That's exactly right. Because often when you're editing one string to another, you want to know why that is. Okay? Can anybody think of an application of why you would want to edit one text to another and see what it was? Yeah? Spell checker. Okay? So a spell checker, it would tell you that your word is misspelled and that the distance between this word and that word is 3. Maybe there you want to know what was the word that minimized it. You don't care about the path. Why might you actually want to reconstruct the changes involved? Maybe to improve your spelling, but let's say if I were to look at your term paper and his term paper, and I find that they're 17 characters apart. Okay? Now I could punish you and say, look, your thing's only 17 characters from his. They say, oh yeah, we'll prove what's the actual difference. And we'll find out, well, look, when I look and find what the edit distance between the document is, the difference is your name is 17 characters longer than his, right? And that was the exact difference between them. Okay? So does everybody see that you want to actually sometimes reconstruct what the actual changes are? For example, one application that I once had, I once worked on an OCR system, or optical character recognition system, where you wanted to scan a page and read what it was saying. Okay? How would we test it? Well, we knew what characters were on the page, right? Okay? Because let's say we have a page, we know what it is, we typed it in. Now, if the program came back, let's say that the word was, me and Bobby McGee. Suppose, as is often the case, an R and an N often look a lot like a, an M. Does everybody kind of believe that? Now, suppose we just match the characters that we did straight on. If the only mistake we made was replacing a me by an R and an N, it would look like we got all the characters wrong. Does everybody kind of see that? Maybe people don't see what I'm saying here. Suppose I know that text is me and Bobby McGee, and I read it as RNE space AND space BOBBY. How many mistakes did I make? I made one. Or maybe you could say it was two, right? It was a insertion and a substitution, right? If I just did it by aligning them up, how many did it actually make? I would have radically overstated the number of mistakes. Does everybody see that? So trying to figure out what is the simplest explanation to make this the same as that is an edit distance problem. Okay? Any questions about that? Any questions about why we need that? Okay? Any questions? So how can we reconstruct what the path is? The easiest way to do it, conceptually, is to start at the bottom corner of our matrix, where our goal statement is, and keep following the parent pointers back. Does everybody see that? It's actually kind of interesting. To fill out this, what is the similarity? It took n times m boxes. Notice the actual path involved only n plus m boxes, right? We didn't know where our mistakes were when we started doing this, right? So we had to compute all possibilities, and then walking back, we could figure out what was the right place where the errors were made. Any questions about that? Okay? So if I give you an n by m matrix, dynamic programming matrix, and I ask you to follow an edit distance to follow back the parent pointers, how much time will it take to follow the parent pointers back? Oh, n? Well, if one of these strings is long and one of these strings is short, the answer is not quite. But I will claim n plus m. Does everybody see that? Every time I move up, I'm either reducing one of the parameters by one or both of the parameters by one. I can only do that at most n plus m times. Okay? Any questions about that? The other thing that is cool, however, is that you can reconstruct the path recursively. Okay, and I want you to look at this. This is just because this is cool and to get an understanding. Suppose I want to reconstruct the path. Once I have the edit distance matrix, what is the path to edit the string S into string T, ending up at position ij? Well, what I'm going to do is the following. Okay? If the parent of the last thing is a match, what am I going to do? I'm going to reconstruct the path up to I minus 1, j minus 1, and then output the last thing, which was a match. If I, output this thing, if it ended on an insert, I will reconstruct the path up to ij minus 1, and then output an insert. If it ended in a delete, I would reconstruct up to I minus 1j. And delete. What's interesting about this recursive algorithm, does everybody see that if I follow the parent pointers back, I reconstruct the path in reverse order? Does everybody kind of see that? What's slick about this recursion is that it actually reconstructs the path in the right order. Why? It outputs the path up to this point before it outputs the last thing. Does everybody see that? Any questions about that? Yes?
Is there a particular reason you don't consider substitution here?
Well, substitution and match are really whether or not, okay, here, it's clear that this meant I came from the diagonal. Does everybody agree with that? If I wanted to output whether it was a match or a substitution, which is a reasonable thing, I would also have to tell whether S sub I equals S sub j, T sub j, right? That's why actually match out probably did that, actually. My subroutine here, match out, probably did that, okay? Any questions? So any questions about how you reconstruct what the parents are, okay? The decisions we made on the way. Any questions? Okay, what else can I tell you about this? Let me tell you that this basic recurrence, I've got, according to this, 3 minutes. Suppose, let's say, I wanted to change my edit distance problem a little to something that seems quite different. Suppose I have a single word, let's say Skiena, and I want to see where is Skiena best fit in the Bible. Okay? I am not in the Bible. I will let you know this right off the bat. Okay? But there is some place in there where there is part of the Bible that is probably has something closest to Skiena. Maybe one of the Old Testament people were skiing. Okay? Maybe there was something else that was happening. Okay? Suppose I wanted to find where in the Bible is there a place skiing. Okay? Where is the place in the Bible that is closest to this? This is a substring matching problem. Does everybody kind of get that idea? How would I change my recurrence relation so that I get a good score for matching whether this word appears, where does this word appear in the string? In general, if we did the full distance of editing Skiena to the whole Bible with the dynamic programming algorithms we stated, let's say the Bible was 3 million characters long. I don't know if that's true or not, but let's say that that is. What would be the cost of editing Skiena to the Bible? It depends. What would the cost be of editing Skiena to the Bible if we had the edit distance as we defined it before? What would happen, yeah?
It would be the cost of editing Skiena to the closest thing that you could find, plus the other almost 3 million.
So what you're telling me is probably what's going to happen is that somewhere in the course of a Bible, somebody used the character S. And a page later, they used a K, and then an I, and then an E, and an N, and an A. Does everybody see that? And what is the edit distance going to be? It's going to delete everything that wasn't that, right? Then match it. Then delete everything that wasn't that. Then match it, right? Do you learn anything about where Skiena is close in the Bible? Okay, I claim the answer is no. Okay? What's interesting, though, is that by changing the initialization condition, okay, you can make this work. Okay? Maybe I'll just say this here. What's the problem? Remember the original cost. What was the edit cost of editing 0 characters